complexity. How new mathematical methods allow for new solutions to everyday problems. Olga Holtz, Berkeley, Princeton, and Technische Universität Berlin.
When the wall fell, I was a schoolgirl in Chelyabinsk in the Ural Mountains. It was an event that changed the world and my life.
I should thank the organizers for putting together such a great event. It's a pleasure to be here, as always. A pleasure to be in Berlin. I will try to introduce a mathematical area that many of you may have heard about, may know about in some detail, and I will try to make precise the notion of complexity, which again should be quite intuitive. We all talk about complexity, right? About our everyday problems. Some things are complex, right? Some things are complicated, so that's what we intuitively understand by complexity. And in fact, in mathematics, the same occurs. Some problems are more complicated than others. So how do you know, mathematicians are these pedantic people who want to quantify everything, and they want to get hold of and understand things really in great technical detail. So how do you understand complexity? Well, you want to solve a problem which typically is a question to be answered, and typically it's a general abstract question, not something concrete. How do I find my way, you know, from my home to the university, right? But something more general. How do I connect 2 points, A and B, say on a network, in the most efficient way? This can be quantified completely precisely, and this becomes a problem, right? There are typically infinitely many instances of a problem. Each has its own solution. So that's what we call the problem. So an instance can be thought of an input into an algorithm. And again, we talk about algorithms. We intuitively know what it means. There is a formalized notion for that, which I'll tell you about in a second. And the solution is an output, right, of an algorithm. So what could be a problem in mathematics? Primality testing is a given number, is a given positive integer prime. You may know what prime means. Primes are the numbers divisible only by 1 and themselves. And these are incredibly important building blocks in number theory and in the whole mathematics. So that's a general problem. This happens to be solvable in polynomial time. Polynomial in the input size, which again has to be quantified correctly. And this was a great achievement about 8 years ago that result was established. Another problem that I sort of mentioned already is the traveling salesman problem. How do you connect several points, let's say on a network, right? You want to visit each point exactly once, and you want to be as economical as possible about it. So you want to minimize the total length. It can be measured in many different ways. You want to minimize the total cost. It's the same problem. The beauty of mathematics is that you can, with one tool, with one mechanism, with one model, understand a whole huge area, a whole class of problems, as we say. So some problems are decision problems where the answer is yes or no, to be contrasted with problems that have a numerical answer, right? A concrete answer like 42, or you know, a path in a graph, something like that. So I did mention how we measure the instance size. We say that, so typically we encode our inputs. They can be encoded as bit strings, and then the typical sizes in bits. You don't have to do that. You can measure it in many, many different ways. A number can be measured by the number of digits in its representation other than the binary, and so forth. You know, so there are many, many ways to do that. And in terms of complexity, you can also understand different things. So what is typically thought of as complexity is the worst case complexity, where you want to see how an algorithm, your procedure for finding a solution, behaves under the worst possible scenario. This can be also compared with average case scenario or the best case scenario. Usually the best case scenario is really not challenging, so you don't want to analyze that necessarily. So what is polynomial time? Polynomial time typically means worst case complexity. Given an input of size n, some function tells you how much time, how much computational time you will spend to eventually arrive at an answer, right? And this is a function of n. If this function is a polynomial, then we say the algorithm works in polynomial time. So this goes back, these notions go back, well, actually, to the people even before Turing, but definitely to the work of Alan Turing, this very profound contributions to theoretical computer science. So Turing formulated first this very detailed notion of an idealized machine, which actually models all our everyday computers today. Every computer you use is effectively an instance, right, of a universal Turing machine. So a Turing machine is something that can be understood, in fact, very simply as a mechanical device. It's an idealized device. It has an infinitely long tape. So there is a tape, there is a head that reads the tape. The tape consists of segments. It's divided into segments. And a series of commands is being executed. The commands are very simple. So you move along the tape or you read something. And you record the states of this machine. So such a simple device, idealized device, is actually equivalent to the machines of today with all these millions of microchips that we use. So there are different subcategories. There are deterministic, non-deterministic, quantum Turing machines, lots of different flavors. And likewise, there are lots of different flavors of complexity measures. As I said, you typically measure the time required or the number of arithmetic operations required, and this is the complexity of an algorithm. So it is, in a very precise sense, a measure of how complex a problem is. And a problem, remember, is not an instance, right? It's a whole class of instances all answering the same kind of question. So as I mentioned already, what we see today started with the work of Turing, led very quickly, in fact, in the 40s and early 50s, to the development of electronic computers. This is one of my favorite photographs, one of my heroes, Robert Oppenheimer, standing with another very, very remarkable scientist, John von Neumann, a darker figure, if you will. And they are standing in front of ENIAC, one of the first electronic machines built according to the von Neumann architecture. This is all at IIS in Princeton, so a very special place and a very special couple of people. Okay, so what does a complexity theorist do? A complexity theorist, or a theoretical computer scientist, tries to provide upper and lower bounds on complexity. So tries to analyze how much time or arithmetic complexity is actually required to solve a problem, and this is quantified. So upper bounds just require you to produce an algorithm that performs with that speed, let's say, and lower bounds are much trickier. They require a very careful analysis of the problem. There is a whole hierarchy of complexity classes. The most famous are P and NP. P is what is doable in polynomial time on a deterministic Turing machine, and NP is the same for non-deterministic Turing machine. So it's a technical division, which is a little tricky to explain. This is one of the most outstanding problems in theoretical computer science. Is P, the class of problems in P, is the same as NP. And the majority of theoretical computer scientists believes that this is not the case. There are many indirect evidences that this is not the case. However, the question is still open, and this question is worth $1 million if you manage to solve it. So, as I said, NP means roughly checkable in polynomial time. So this deserves a long discussion, but I will not go into this. As I said, there are many important everyday problems that are in fact NP-complete, which means that if this problem happens to be solvable in polynomial time, then this is a representative of the entire class of NP. And in other words, if you manage to solve it in polynomial time, then you solve all NP problems in polynomial time, which would be a very stunning result, and I'm not sure we are ready to see that. So as I said, the majority believes that's not going to be the case. This is a solution, a particular solution in this small picture of the traveling salesman problem for 15 big German cities, the biggest German cities. All right, so now finally, what do I do with my collaborators? We are analyzing a slightly different flavor of algorithm performance, namely complexity in the sense of communication. When we have a problem so large that many computers or many processors have to deal with that. In that case, we want to analyze how much communication is required. So how much different processors have to send information to each other and receive information from each other, which we call communication complexity for algorithms. Our goal, of course, is to minimize energy costs and time costs. This is becoming the next bottleneck, not so much the arithmetic complexity that I just told you about, but the communication complexity that we are now trying to analyze. There are many different computer architectures. In all these instances, one has to somehow figure out what is possible in principle, right? And what is intrinsically not possible, like in the arithmetic complexity setup. And that's very recent work. My co-authors are mostly in Berkeley, Gray Ballard and Jim Demmel, also Odette Schwartz, who is currently at Weizmann Institute in Israel, but coming to Berkeley very soon. So we have been building a framework to make this analysis possible, much in the spirit of arithmetic complexity, and we are quite happy that we were able to analyze, in fact, most of the linear algebra algorithms that are used everywhere, you know, for problems of control theory, computer-aided geometric design, you name it. Scheduling, logistics, and so forth. What we could do, we could show that many things are optimal already and many things can be optimized, and we also established intrinsic bounds as to how far you can go, things you cannot go beyond in the sense of lower complexity bounds. So another exciting thing, which I unfortunately cannot explain to a general audience, we were using lots of different tools, some from analysis, some from algebra, and some from combinatorics. In particular, we borrowed the very important notion from graph theory that has to do with graph expansion. It's a notion about local properties of a graph, connectivity of a graph. And we analyze these massive graphs that are computation graphs coming from, it's like a scheme of an algorithm, how the algorithm is actually going to be performed. This can be all analyzed through a graph as well. So graphs can be analyzed using algorithms, right? And algorithms can be analyzed using graphs. So combining all these techniques, we have been able to do some of the analysis that is quite important, becoming quite important now. And there are lots of questions that remain. This is all related to not only to theoretical computer science, to mathematics, it's also related to engineering and problems of design, as we've seen before, like in the traveling salesman problem. So lots of challenges remain, and I will be happy to discuss this in detail if someone is interested. Thank you.